Hi guys, Mr. Kane here.
Hi guys, Mrs. G.
So we're talking about calorimetry today.
Okay.
And calorimetry and using heat capacity to measure calorimetry.
Right, they're kind of related.
Basically what calorimetry is, it's the study of the measurement of heat flow, how heat goes from one object to another. And we use a device called a calorimeter to do this measurement.
Yeah. And for us, calorimeters are nice, cheap, stacked styrofoam coffee cups.
Yeah,
they're insulated.
They're insulated, right? We basically just want to ensure in a calorimeter that you're not losing any heat to the surroundings. You want to try and keep your keep what you're measuring to be where all the heat stays.
Right in the coffee cup.
In the coffee cup rather than outside of the coffee cup, which is why we use coffee cups, because they're fairly well insulated.
Yeah, they're well insulated, and two of them even better than one.
Mm-hmm. Our calorimeters that we use measure with constant pressure, right?
Right.
And they measure a change in enthalpy at delta H of the reaction. The way they do this is they measure a delta H by measuring the Q of a reaction.
Right.
And we know that Q is equal to ms delta T. So if we can measure the mass, the specific heat capacity, and the temperature change of a substance that's undergoing a heat change, you get the Q.
Which is energy, which is enthalpy at constant pressure.
Mm-hmm.
Yep. Okay, so here's a question for you, Mr. Kane, with calorimetry. We use a calorimeter, which is a coffee cup calorimeter. How do we get, like if we were to throw like a salt in water, how do we take the initial and final temperature of the salt after it's been placed in water?
Well, notice with the way that we've got this set up, we only need to actually measure the delta T of one substance.
Yeah.
If you've got a coffee cup full of water and you can't measure the temperature of salt because salt's not a liquid, you could measure the initial temperature of the water, throw the salt in, and then measure the final temperature of the water, and now you've got a temperature difference for water.
And whatever the water does, the salt did the opposite.
The salt did the exact opposite, right.
Ooh, so a flow of energy into the water.
Right, exactly. If the water has gained some energy, it's got a positive amount of energy, then what winds up happening is that energy has to have come from somewhere, so it has to have been lost.
From the salt.
From the salt.
Okay.
So a gain of energy by the water is a loss of energy by the salt.
Ooh, that's starting to look like MSAT equals MSAT.
Yeah, yes, it does.
Wow.
All right, so since the change in energy is equal to Q, and energy is not lost or gained, but is transferred, then the energy lost by the hot substance is going to be equal to the energy gained by the cold substance.
Okay.
So that means that if the two Q's are equal to each other, we could set up an entirely different equation using MSAT.
Okay.
The MSAT had half of the equation. So MSAT of the hot, the temperature lost by the hot object, is going to be equal to the temperature gained by the cold object.
So calorimetry technically uses water to research the energy transfer of other substances to the water.
Correct.
Substances that are not so easy to take the temperature of, like a block of metal.
Exactly.
Okay, so if I'm getting this right, the thermodynamic law says you cannot gain or lose or create, so whatever the metal loses, the water gains the exact same amount.
Correct.
Oh, okay.
Yeah. That makes sense, right?
Yeah, that does.
That actually helps us to measure the temperature change of various objects.
Looks like an awful lot of algebra, Mr. Kane. Hey, there's our expensive calorimeters.
Yep, very expensive. 2 coffee cups, not just one.
Yep, we stack them together.
And notice you got to get the kind that has a styrofoam cover. It's nice to have a styrofoam cover anyhow, because then heat doesn't rise off.
Yeah, you don't want to lose heat to the atmosphere.
Nope, because that's the surroundings.
Yep.
All right. So water is usually used as our heat sink because it absorbs energy so well, and also probably because it's so abundant.
Yeah, plentiful. You can take the temperature of it easily enough.
We know the specific heat capacity is 4.184 joules per gram degree Celsius, so we don't have to figure that one out. So it's pretty nice to be able to use water. In using a coffee cup calorimeter, basically here are the steps. First, you start out by wanting to know the initial temperature and the mass of the water that you're placed in there.
Okay.
Because you got to know ms delta T, right? So you know mass, specific heat, and temperature change, so you got to know the initial temperature.
And the beauty of water is its density is 1.0 gram per milliliter, so however many milliliters that is, that's the mass.
That's the mass.
Nice.
Okay. Step 2, get the mass of the unknown object. Usually that's a solid. It could be a salt, like you alluded to earlier. It could be a piece of metal that you want to know the specific heat capacity of, or any object that you want to know the specific heat capacity of. You heat the object up to a known temperature. Now that might sound tricky, but if you place the object in boiling water and you leave it in there long enough, you know it's going to be about 100 degrees Celsius.
Yeah, because if it's in boiling water, whatever the water's boiling at, that's the temperature of the object, right?
Right, and the fact that we know is that water boils at 100 degrees Celsius. Step number 4 here, put the unknown into the water and wait for them both to reach the same temperature. So you just plunk it in there and you leave it set there for a little while until the temperature stops changing.
So if we put a hot metal in the water, I'm going to assume the water in the coffee cup calorimeter will increase in temperature.
Right, because the water was room temperature water when you started.
Right.
You toss a piece of metal in there, hot piece of metal. It's going to get, the water's going to get warmer. The piece of metal is going to get colder.
Right.
The water's going to get warmer until it reaches the same temperature that the piece of metal is.
So the final temperature
as the metal's
is the same.
coming down. Yeah, and both temperatures wind up being the same final temperature.
Okay.
Okay, it's the same for the water and it's the same for the piece of metal or the salt or whatever it is that you put in your calorimeter.
So whatever energy the water gains, the metal lost the exact same quantity.
Exactly.
Got it.
And then you can just use the concept of the loss of energy of the hot system is equal to the gain of energy of the cold system.
Okay. Oh, that's a lot of words.
That's a lot of words, yeah. Okay. So we're going to need this piece of information here, the specific heat capacity chart. So if you have that in your notes, you might want to reference that later. But here we go.
All right, so the whole idea behind calorimetry is that the energy of the metal, which is the hot substance, will lose to the water. And the water gains, correct?
Right.
Okay, so that's the negative MSAT of the metal equals to a positive MSAT of the water. And all we have to do is fill in the right stuff.
Right.
Okay. So the mass of the metal was 15.0 grams.
So 15.0 times, we don't know the specific heat.
That's our unknown.
Times the delta T, what was the final temperature?
Final minus initial. The final temperature of the water and the metal, 29.5 degrees Celsius. That's the final temperature of both.
And what's the initial temperature of the metal?
The initial temperature of the metal was 100.
How much water did we have?
50 mils, which is 50 grams.
Specific heat capacity to water, I've got that memorized already from all those problems we've been doing.
Right, and the final temperature of both of them was the 29.5, but the initial temperature of the water was room temp, which was 25 degrees.
Okay, so let's see, 29.5 from 100. Might as well multiply that by 15.
Yep, times that by 15. That's going to be a negative 1057.5.
Times S is equal to, now we can do this, 29.5 minus 24.
4.5, and
multiply
then
it by
multiply that by
4.184.
4.184 times 50. That comes out to be 941.4.
Okay, and we'll divide both sides by the negative 1057.5.
Well, the negative sign actually goes away, Mr. Kane. 29.5 minus 100 cancels out.
Okay, so before I divide, I think I noticed something that I messed up here. This is a negative temperature change, right?
Right.
And that's a negative sign, so it's two negatives, so it winds up being positive.
Right, because you can't, the negative sign is there basically for the algebra, because you can't have a negative specific heat, you can't have a negative mass. So when you take that 29.5 minus 100, you get a negative change in temperature, which multiplied by that negative sign in front of, it's an algebra issue.
It just comes out in the wash.
Right.
And I divide both sides by 1057.5, and we wind up with an S of
0.890.
0.890.
And that's joules per gram degree Celsius.
Thank you. That's what I was just going to ask.
Yep.
Now, I got 0.890 joules per gram degree Celsius. The problem says find the specific heat capacity of the metal and the identity.
Okay, so we found the specific heat capacity. Now we have to ID it. Let's see, 0.890, 0.890.
Yep, there it is.
Aluminum.
Done.